All right, so now we're going to check with the help of a computer that what I told you about the general element of the Lorenz group, this exponential expression of the general element of the Lorenz group, is exactly what I told you it was. And that is also compatible with all that you knew in previous courses about Lorenz boosts and rotations. Let's get to it. All right, so this is a mathematical notebook that will help us do the calculations that we need to do in order to show what we want to show. Now, the first thing that I have here is the lambda tilde matrix, even though I call it lambda, but it's the lambda tilde matrix that implements a boost from a reference frame to another reference frame that has a relative velocity v, and v is a vector here. This lambda matrix that I have here is the same one that we derived in class, as you can tell. That comes from the general Lorenz transformation that we derived in previous videos. So let's run this matrix. And in particular, let's particularize now to a velocity that only has a v component in the x-axis. So there's only capital V is the value of the x component of the velocity, and there's 0 component of the velocity in the y and z axis, right? The z directions. So if we compute the matrix lambda, in that case, we obtain exactly what we obtain in class, which is gamma minus v gamma divided by c, and gamma, and then the identity here. So nothing happens to y and z, and there's the usual expression for the Lorentz transformation between t and x. Wonderful. Now, one thing we can quickly check is that indeed the passive transformation and thus the active transformation. So if I do a transformation with a velocity v and a transformation with a velocity minus v, and I compute the matrix product, I should get the identity. If I do it, I get this matrix, which happens to indeed be the identity once we substitute gamma by the gamma that is as a function of the velocity, right? One of the Lorentz factor, 1 over square root of 1 minus v squared over c squared. Very nice. All right, so having established that these are the same matrices we obtained in class already, now let's play with them. Let me consider the interval for vector delta x. So this is the interval, the vector basically connecting two events. Now I can transform it with this Lorentz transformation only in the direction of the x-axis. That does this, of course. This is the expression that you get when you transform, and indeed is the Lorentz transformation that we know. All right. Now, why did I did this interval, or this, if you want, for vector, the difference between two positions for vectors between two events? Well, because once you compute the inner product, the norm of this vector, you can tell that is exactly the space-time interval. This is x sub mu. You see how the zeroth component changes sign. X super mu contracted. When I do that, I obtain indeed the space-time interval, as you can tell here. Now, I do the same with the transform version that I got, and I should get the same, because the space-time interval is invariant under the Lorentz transformation. So if I did things right, the expressions should be the same. Are they the same? Well, even though they may not look the same, let's simplify though. Let's now substitute, let's do it again. Let's do the expression, this operation again, but now substituting gamma by the Lorentz factor. And we see that indeed it is the same thing, right? This actually shows that this expression, this norm of the interval between two events, which is the space-time interval, is exactly the same in both reference frames. Okay, so far so good. Now, the main objective of using this notebook is to actually write the Lorentz transformations as this exponential of minus I, the rotation part if you want, and the boost part, okay? So let me just define the infinitesimal generators of the Lorentz group, okay? And the Lorentz transformation as a function of the rapidity and the rotation vector. Now, let's do first a pure rotation. So we have this full matrix here, and let's do first this pure rotation. This is a rotation of angle alpha around the z-axis, as you can tell. And there's no boost. All right, so let's find the matrix form. And look at that. Once you substitute these vectors in here, and with these generators, what you get is that the expression is indeed what I promised you it was, is the rotation matrix around the z-axis. Wonderful. It does nothing to time, and it rotates in the z-axis, changing x and y. Okay, in the x, basically it's a rotation in the xy plane. Wonderful. Let's do now the pure boost. So this is the other extreme. The other extreme is no rotation, and as you can tell, the rapidity has component theta, and this theta only a component in the x-axis. Let's see what it looks like. And there you go. As you see, you have the hyperbolic rotation, something that looks a lot like a rotation, but with hyperbolic sines and cosines. You have the hyperbolic rotation between time and x, because there's a velocity in the x-axis. Now, we have done the Lorenz, the pure boost, we've done in two ways, with these Cauchy and Singe expressions, and also we did it with the formulas that you learned back in the day in class, if you want, I mean back in your previous courses, that gave you this. These are supposed to be the same thing. The hyperbolic sine and cosine and this matrix are supposed to be the same. One came from the formulas that you learned in your previous courses, if you want, and also in this course, and this other one came from using the exponential expression, which is the one that is arguably better, right? Okay, so let's see that they are the same. So, express as a function of rapidity and recovering the expression for pure boost at the beginning of the notebook. Again, we have that the rotation vector is 0, so no rotation, and then we have a rapidity that is equal to this amount, where v is the velocity that we have in the x-axis. Now let's compute the matrix form, and it's like that. Well, obviously this expression here, that you can see here, right, is exactly the same as this expression here, and we're done. I don't expect you to believe it. Let's just copy this one and put it next to the other and see if they're really the same. Do they look like the same? Well, maybe not. So I think I need to work a little bit more to actually convince you that these expressions are the same. Okay, now I copied this. Well, actually the first thing that I'm gonna do is I copied this here and I'm gonna tell it to simplify. But to simplify first, let's see what is the exponential of the hyperbolic arctangent of x, right? Because that's what we have, exponential of minus arctangent of v divided by c. What is this? So if we do that, we can tell that the exponential of an arctangent simplifies a lot. And we can actually do this simplification by hand here, right? If we simplify this expression like that, we obtain that, okay, let's write it in matrix form. We obtain that the expression is this one. Now let's go back to the original expression that we had, and let's compare. And indeed, if you check, you see that this is exactly the gamma factor. This is minus b gamma divided by c. You see, it's the same thing. This is the Lorenz factor, and you obtain minus v gamma divided by c as well, and here just gamma. So indeed, the two expressions are the same. The expression in terms of hyperbolic sine and cosine, the expressions in terms of hyperbolic sine and cosine are exactly the same as the expression that we got from the pure boost from the formulas we derived in class that are more related to what you knew in previous courses. And I hope that that convinces you that this expression is better, more powerful, more general. You can do any rotation or boost with the matrix expression using the infinitesimal generators of the Lorenz group. Something interesting to mention is that these generators should remind you of something. If you take the 3x3 sector here, here, and here, for those of you who have seen it, those are the generators of SO3. And these ones are the generators of the hyperbolic rotations. Now that we have understood that the Lorenz group is nothing but rotations, if it's spatial rotations, it's rotations as you know them, and if it's boosts, it's kind of rotations by an imaginary angle. Let's see what are the consequences of this and what a Lorenz transformation actually does to a reference frame and the access of two different reference frames. All right, so I prepared a little presentation here about the Lorenz group, how it acts, what it does, and some of the fun implications that considerations about it have. Now, what I wrote here is the general expression of the Lorenz boost in terms of, you see, the generators of rotations if you want to boost, so the generators of the Lorenz group. And as we talked about, we have the rapidity here, and we have the rotation vector, right? And then we have here the structural constants of the group. This is the algebra that generates the group. All right, so now one thing that is interesting and is worth mentioning is, as you saw in the previous slide, boosts and rotations don't commute. The Lorenz boosts in 1 plus 1D, they commute, but that is not true in 3 plus 1D. When you compound two non-collinear boosts, in general, that is not a boost what you obtain, but a combination of a boost and a pure rotation. And that actually depends on the reference frames. And this is kind of cool. This is a phenomenon called Thomas precession that I may even ask you about in assignments. I don't know yet. But it's interesting, and it's actually important and necessary to interpret outcomes of high energy physics experiments often. But you can see that actually we can rotate things by using boosts. You do two boosts, something that are pure boosts, and then you end up with a boost and a rotation. And that actually is not something that happens in Galilean physics. Now, one thing that is important to remember with this is that how much of a boost you have and how much of a rotation you have when you have a combination of two boosts or a boost or a rotation is something that depends on the reference frame. Different people would disagree on how much of a boost or a rotation you applied. This is something that happens only in the Poincaré group and not in the Galilei group. And the key for that is this particular commutator. This particular commutator here for the Galilei group is 0. Whereas for this group, for the Poincaré group, is non-zero. All right, so now after having talked about Thomas precessions, let's see what the Lorenz transformations actually do to the axis. Let's focus on 1 plus 1D, let's focus on the X and T as a subspace if you want, and let's do a boost in the direction of X. So this is a pure boost in the direction of X, as you can tell here. And let's see what it does to the axis. Well, it's a hyperbolic rotation. So I borrowed this super nice plot from Wikipedia, where you actually can see that the hyperbolic rotation, what it does is the rotation generated. So it's a transformation generated by these hyperbolas, right? So what it does is tilt the axis. You see, this is the original CT and X axis. So the axis is being tilted like that when I do a boost. So X, if you want, rotates or is tilted counterclockwise, and the t-axis is rotated clockwise. So these are the new axes as seen from the reference frame that is not boosted. So you can tell that the axes tilt, and they get the larger the velocity of the boost, the closer they get to 45-degree lines. All right, a little bit of a reminder. We define in class and also in the notes in this equation the space-time interval, and we classified intervals, the relationship between two intervals, based on if they're space-like separated, if the space-time interval is positive, time-like separated, if the space-time interval is negative, and null separated or like separated if the space-time interval is 0. Now, this is actually really an important classification, and we will understand why in a second. So I have two events here that are space-like separated. You can see that in this frame, Tx, these events have more spatial separation than time separation. So they're space-like separated. Now, here's an alternative definition of space-like separated events. Two events are space-like separated in special relativity if I can find an inertial frame in which the two events happen simultaneously. Now, can we do this for these two events? Yes, indeed. If I do the hyperbolic rotation corresponding to a Lorenz boost, I tilt the axis like that, and there is indeed a frame T prime X prime for which the two events are happening simultaneously. You can tell this is the plane of simultaneity. T prime equals 0, and you see that the two events happen exactly at T prime equals 0. They're happening simultaneously in the prime frame, even though they don't happen simultaneously in the unprime frame. Now, we can do something similar for time-like events. I have now here two events that are time-like separated, as you can tell. The spatial separation, which is this, is smaller than the time separation, which is this. Of course, they happen at different positions, but an analogous definition for time-like separated events is two events are time-like separated if I can find an inertial frame in which the two events happen at the same position. And indeed, if I do a Lorenz boost here, I can find a frame, a prime frame, in which the two events are happening at the same position. And in particular, this is the position X prime equals 0 at different times. Okay, so yeah, this is the difference between time-like separated events and space-like separated events. Space-like separated events, you can find a frame in which the two events happen simultaneously. Time-like separated events, you can find a frame in which the two events happen at the same position. So now that we have understood the difference between time-like and space-like separation, let's get a little bit more familiar with space-time. I mean, we're going to do a little bit of a tiny little game. So what is the representation of motion through space-time? When you move through space-time, so imagine that you are two people, right, here and here, and you're at rest. Being at rest, what does it mean? That means that you don't move in space-time? Well, not true. You do move in space-time. You always move towards the future. So yes, if you're not moving, quote unquote, then you still move towards the future. Indeed, we can communicate, and to communicate, we send, for example, light to each other. We send signals to each other, and this is what happens when I send light to you. The light arrives. I send the light in the past, but it arrives to you in the future. Fair enough. At the speed of light, of course, which is the 45-degree line in this space-time diagram. Now, moving slower than light with some constant velocity would be something like that. And you can tell that moving slower than light means that your trajectory is a time-like trajectory. The tangent vector to that trajectory is a time-like vector. That's important because your forward velocity, the forward velocity that you have is the tangent vector to your trajectory, and you can tell that if you move slower than light, then your trajectory, the tangent vector to the trajectory, will always be a time-like vector. Will have more time component than it has spatial component. If you were to move faster than the speed of light, then your forward velocity would have a tangent vector that would be space-like. You see, we'll have more spatial component that has time component. And in special relativity, that is not allowed. In general, is it allowed in general relativity? We will discuss that later on in the course when we talk about something called the energy conditions. But for now, let's keep it as is. Let's keep the mystery. So let's talk about the twin paradox. We know, of course, that in space-time, we can have and we can compute difference in time and difference in space as measured by different frames. Typically, the example that is the most known in popular science even is the twin paradox. So imagine you have two twins. One of them is going to travel in a very fast ship to Alpha Centauri. Alpha Centauri is about 4 light years away from us. So imagine that person travels at 0.8 the speed of light. And then, of course, the brother that stays at home makes a prediction of how long it will take. So the distance is 4 light years. And then, of course, the mission time, it would be twice the distance divided by the velocity of the ship. Why twice? Because there's a go trip and return trip, right? Well, computing it, you obtain that the duration of the mission will be 10 years. All right. However, what happens from the point of view of the brother that leaves? So imagine that the brother is traveling, and suddenly the brother, after 3 years, he realizes that he's arrived to Alpha Centauri. And he's like, hold on, what? No, I was supposed to take 5 years to get here. How come I got here in 3 years? There's something wrong. We measured the distance wrong. Oh my God, we measured the distance should be something like 2.6 light years, not 4. Jesus, not 4. Oh my, I need to go back and tell everybody, how could we measure distance wrong? We're really good at measuring distance between like stars that are not really far away. We have parallax, we have really good techniques. I need to go back because something is really wrong. And indeed, the brother comes back, and indeed the whole trip takes 6 years for the brother, and the brother arrives and then tells the brother that stayed at home, is sitting at a chair for dramatic purposes, say that the brother is facing a computer, so not seeing his brother that traveled. And then the brother that traveled says, hey, you won't believe it. I only took 6 years total to be there and back. So that means that Alpha Centauri is 2.5 years away from me. And then the brother turns around and is older. I mean, allegedly only 4 years older, but it could be more if he were faster. And the brother says, what do you mean? You've been away for 10 years. So again, this is the typical twin paradox that everybody has heard about. And it tells you that, of course, the time intervals, right, are relative, and the spatial intervals are relative. One of the brothers can say Alpha Centauri was actually closer. And then we can understand this in terms of length contraction and time dilation. But here's something that is often missed in the most popular science explanations about the twin paradox. What makes the brother that goes special? At what point is different from... Because you see, you can actually think that instead of being the spaceship that moves with 0.8 c, it could be Earth that moved away from the spaceship at 0.8 c. What makes the difference? Why one ages and the other not? What makes one of them special? Because in a boost is equivalent. The one who's boosted is a choice. Which one is the one that's boosted? Well, the difference, and here's a geometric geometric view of the twin paradox, what makes the difference is actually this. It's not often is said, it's the fact that one accelerates on Earth. No, it's not quite that. It's the fact of, it is certainly the acceleration, the difference. One accelerates and the other doesn't. But in the simplest case, imagine, that one of the brothers was already moving and they just synchronize their clocks here. The important bit is this point in the trajectory. If the trajectory is mostly inertial, you may do, one of the possible assignments could be a realistic version of the twin paradox with accelerations, with proper accelerations all the time. But imagine that it's inertial and they only just, when it arrives, just turns around and accelerates really fast as compared to the duration of the trip. So this is the point that breaks the symmetry. And you can tell that if you count the birthdays, imagine that the dots are birthdays in a way, you can tell that the simultaneity planes that go because of the Lorentz transformation. There was a hyperbolic rotation that tilted the x-axis. Now, when you turn the other way, the axes are tilted in the opposite direction. And at this point, you see, you're going to be missing 2 birthdays. You're going to be missing time. Here, you can tell that is this point. Otherwise, if they had continued, there will always be 1 birthday for one birthday of the other. And it's all relative. What makes the difference between the two, what makes one special, if you want, is the acceleration point. So this is actually important and very easy to see if we do a geometric interpretation, if you want, of the Lorentz transformations. Another point that I want to make is that, of course, the notion of simultaneity is relative. And we're going to make a big deal out of that, above all to battle another misconception often talked about in popular science. Now, simultaneity is relative. 2 observers in different state of motion would not agree about what happens first. We have 3 events here, right? A, B, and C. And we have 3 people here at point B. At point B, we have 1 person that has 0 speed with respect to this axis, and then a person that will have some speed to the right, and some person that will have some speed to the left. For the person that's moving with this axis, that person would say A and C are simultaneous. They happen at the same time, t equals 0. But then the person that moves, those are the planes of simultaneity, and these are the planes of simultaneity for people that move with different relative speeds with respect to those axes. And you see the effect of the hyperbolic rotation, of the Lorentz boost. And you can tell that for the people, for the person that is moving towards the right, then for the person that moves towards the right, C happens first. And then for the person that moves towards the left, A happens first. So the notion of simultaneity is relative. Now, this is really important when we are going to consider a couple of things that are often said in doing popular science of quantum mechanics. So let's see. Just a tiny little bit. It's a little parenthesis about quantum that I hope is a bit entertaining. Now, when this is actually an interesting point to illustrate how popular science was done and how it is done now. This was actually in the front page of the New York Times when Einstein, Podolsky, and Rosen published the EPR paper in 1935. And you can tell here, popular science is, honestly, I mean, that's something we need to do to do popular science properly. Look at that. Einstein attacks quantum theory. Okay, sensational headline. Let's see. Scientist and 2 colleagues, well, I guess Podolsky and Rosen were not scientists, we're just the people who, I don't know, the people who brought him drinks. I have no idea. 2 colleagues find it is not complete, even though correct. It's not complete, even though correct. I mean, it could be better. It's not that horrible. But then this is one belief. A whole description of the physical reality can be provided eventually. All right, this is not that bad. That kind of goes along the lines of what was kind of said in this paper. But look at that. They are given, actually literally given their 2 cents on this. And scientists and 2 colleagues, that gets me. Things have not improved in time. Here's something, this is this is taken from a real medium. It's called popular science. Look at that. The race to prove spooky, quote unquote, quantum connection may have a winner. Entanglement breakthrough could lead to unhackable internet. This kind of follows all the rules of how to be sensationalist doing popular science. Entanglement, buzzword, breakthrough, of course, cool, could lead to unhackable internet, something that sounds cool and everybody can relate to. And then I'm sorry, Devin Powell, this is just, I don't think that you are particularly bad or anything. This is something that happens to many people doing popular science. But look at this, particles don't obey the same rules as people. Okay. That is good to know. Poke a particle and another one far away can instantly respond to the touch without any messages passing through the space between, as if the 2 particles were one. Entanglement is what quantum physics calls the intimate connection. I mean, no quotes, but there should have been quotes there. Of course, you know, in all the quantum courses you've taken, the first thing that you learn is the proper name for entanglement is intimate connection. Einstein called it spooky. This is correct. To his dying day, he refused to believe that nature could be so unreasonable. So same as the New York Times one, it ends with something that is okay. But then everything else, well, this is a video. It's going to go out there, so I'm not going to just say too many bad things, but it's certainly not a great job, in my opinion, of doing popular science. Now, I'm going to take issue with this notion common in popular science of instantly responding to the touch. Certainly, that is not entanglement. When I teach quantum theory too, I do discuss about how this notion is actually inconsistent with quantum mechanics, but it's also incompatible with relativity. Because of the course we're in, we're going to talk about the incompatibility with relativity. But first of all, let's understand a little bit better what entanglement really is. I know this is not a course on quantum mechanics, but I think it's worth thinking about it in context. And as physicists, this is something that morally you should know, because if you end up advising or even doing popular science, you should not make the mistakes that these people are doing and making. Now, quantum entanglement versus classical correlations. Now, here I'm gonna do a little tiny trick. I'm gonna put a black ball and a white ball in a paper bag, and I'm gonna tell you, please grab one and don't tell me which one it is. Don't show me. Of course, you saw that, same as me, that we put only a black ball and a white ball there. And then I'm going to do a trick. Okay, without looking, I'm going to go to Alpha Centauri. Now, I go to Alpha Centauri, and I say, from the distance, I'm going to guess the outcome of the measurement when you measure yours. I grab my ball, and it's white, my ball, and I look at it and I said, oh, your ball is going to be black. Do you think that people would be very impressed? But look at what I'm doing. I'm measuring my own ball, and then suddenly I'm guessing the outcome of the measurement that you do on your own ball. Is that impressive? No. The fact that I know the outcome of the measurement that you will do on your ball is related to the fact that there were correlations. The color of the two balls were correlated. Those are classical correlations. And you see, measuring at a distance, I can still guess what the color of your ball was. What would be way more impressive is if I actually put in the bag 2 sets of dice like that, and then, I don't know, I take one, and if it were classical, right, if I throw it and I get a 10, I have no freaking clue if the dice are actually fair. I have no clue about what you will get when you throw your own dice, right? However, if these are quantum systems and they're in an entangled state, it is possible for me to actually get an 8, and then guess that when you throw, you're going to get an 8 as well. That is what makes entanglement different from classical correlation. So entanglement is a particular kind of correlations that do not exist classically, that tell you that no matter what I do, my outcome will be correlated with yours, even though they are locally random. And if you want to understand this in terms of something classical, well, I'm sorry, you can't. This is genuinely quantum. If you want to know more, again, advertising again, Quantum Theory 3, where we will discuss about classical theories that can have entanglement and what's with that. Anyway, there is no way to understand this in a purely classical context, because you have something that is locally, my dice are definitely fair and random. I don't know what the outcome will be, but I know whatever it is, it will be equal to whatever you obtain or will obtain. My problem comes when people claim that the first person who measures collapses the state of the dice. It's like, oh yeah, Alice measures first, and then there's the spooky action at a distance. You poke one particle, as this popular scientist said, you poke one particle, and then the other one feels it. That is utterly not right. You cannot say that. And well, why not? Well, remember relativity, right? Imagine that the two events of measuring happen in space-like separated regions. Like somebody does it right now in this frame in Alpha Centauri, and someone else does it in front of me. They're space-like separated events. So people, 3 different people, will tell you, all right, B would say, oh, they actually measure simultaneously, so nobody collapsed it. And then the person that moves towards the right would say, what do you mean? C measured first and collapsed the wave function and affected the outcome of A when I measured after. But then the person moving to the left with this velocity, half the speed of light, would say, no, hold on. What do you mean? Was Alice the one that collapsed the qubit of Charles? And then is Alice the one that did the spooky action at a distance on Charles? You see how this is very, very incompatible with relativity? All right. This is all I will say about entanglement. We can discuss a little bit more either in the question sessions, in the live sessions that we have, or in other courses that are actually about quantum. But I think it's important to, every time that you hear that entanglement is related with action at a distance and spooky action, you say, well, actually, no. You may know already this, but this is something recurrent in popular science. So please combat it when you see it. Indeed, the notion of collapse in quantum mechanics is a wrong notion. It's definitely a convenient fiction, something that sometimes is convenient, the same way that Newtonian physics is convenient to explain the mechanics of a car going on a road without actually using quantum mechanics or relativity. But collapse holds no bearing in the notion of physical reality. Instantaneous action is incompatible with relativity, and not only that, it's inconsistent. In fact, collapse of the wave function is inconsistent with quantum mechanics itself, even without relativity. In any case, this is all that I wanted to tell you for this video. I hope it was illustrative and helpful. And I will see you again for the next video, in which we will talk about Nether's theorem. We're going to talk about conserved quantities for momentum, energies, angular momentum, and we're going to set the basis to start talking about the dynamics of relativistic particles. See you then, and until then, take care.